In this video, we're going to mix together two elements, but we're going to do it in two different ways. The elements are iron, which we have here, some powdered iron, and sulfur, which we'll work on next. I'm putting some amount of powdered iron in here. I'm weighing out 7 grams approximately, 7 grams to be a little precise about it. So that's my iron. Now I have sulfur. This is an element on the periodic table. It's a pure substance. It's kind of got this yellowish appearance to it. And it's a powder. It looks a little bit like cornstarch. I'm going to weigh out about 4 grams of this. A little extra. All right, that's pretty close to 4 grams. And this sulfur is a little bit lumpy, so I'm going to use a tool called a mortar and pestle to grind it up and make sure I get rid of the lumps so that I can get a good mixture between the two. So I just grind this up. This is an old-fashioned tool that's been used for many, many years for making powder out of things. Okay, that's probably most of my sulfur. Now I'm going to add my iron to the sulfur so that they're both in the same container. And just stir the mixture up. Just making a mixture. So it's really hard to distinguish, is this a heterogeneous mixture or a homogeneous mixture? You can clearly see that there's not one thing in there. But if we ground it up a little bit finer, if we put this back in the mortar and pestle, it might be really hard to tell if it's heterogeneous or homogeneous. It might just look like some yellowish gray stuff. It's actually, we know its history, we know that it's a mixture of two things. So one of the things you always want to think about if you have a mixture is there a way that we could separate the mixture back out into its individual components? So here's what we're going to do. We're going to take advantage of the fact that iron is magnetic and it should respond to this magnetic device, magnet, but it's not, sulfur is not magnetic. So I put this inside of a bag just to make it easier to clean later, and I'm going to hold it over the mixture. And I'm not surprised to see that I was able to pick up the iron and the sulfur mostly stayed behind. So this isn't going to be 100% effective because obviously I can't attract all the iron. There's still some in there. And you can see there's some yellow flecks of sulfur that kind of made their way in with the iron. And it might be really hard to get them out of there. But if I tried really hard, I could at least get all of the iron out of the sulfur. I may not be able to get the sulfur out of the iron, however. I'll just pull the bag away from this magnet, and I should be able to recover the iron back into my mixture. So I'm going to stir this back up again. Recreated my mixture, and now I'm going to put this mixture inside of this test tube. So I'm going to sprinkle my little boat up here. Pour this compound in there, or this mixture in there. So inside the test tube now I have some iron and some sulfur all mixed together in fairly fine mixture. Here we have a mixture of two solids, like the sand and sugar that we saw before. So we have different crystals of different types that contain distinctly different particles. The sulfur is yellow and the iron is kind of black, so when we mix them together we get this sort of dirty yellow color. If we could separate completely by using the fact that iron is magnetic and sulfur is not, we would find that on the tips of the magnet we have the crystals made of particles, the particles made of particles of iron, and the yellow sulfur particles made of particles are left behind. So that's another separation technique. Like all separation techniques, it makes use of the fact that the properties of the two things that are mixed together are different in some way that allows us to separate them. So we've seen that there are two kinds of mixtures. There's heterogeneous mixtures and there are homogeneous mixtures, or some people say heterogeneous and homogeneous. These kinds of mixtures are categorized by what our eyes can do to tell if they're mixtures or not. Heterogeneous mixtures are the kind that our eyes can tell. Just on the macroscopic scale, we know, even without knowing the history of the substance, that that's a mixture because we can visually see that there's more than one thing in there. On the particle level, that means that the particles for some reason are not mixing into each other. It could be that they're two solids and the particles are just too large to fully mix into each other. But it could also be that there are two liquids that happen to like sticking with each other or with their own kind of particle rather than being attracted into the group of the other type of particle. Examples of this would be salad dressing, like olive oil and vinegar, like the old Italian type of salad dressing. You can see by looking at it that there's more than one thing in there. There's going to be a vinegar layer that floats to the bottom and oil layer that rises to the top, and then you can probably also see a bunch of herbs and spices and things in there too. It's very clear to see just by your eyeballs that this is a mixture. Another example, kind of a similar idea, it's food, would be some kind of soup. Like here's some vegetable soup. You can see pieces of carrot and this looks like some kale or broccoli in there maybe. Maybe some pasta. There's a lot of different things in the soup. It's very obvious by looking at it that this is not just one thing. This is a heterogeneous mixture. Gravel would be another example. If you look at gravel, you can see there's a number of different kinds of rocks that make up this gravel sample. And even if you looked closely on some of the rocks, you might see that within the rock there's more than one type of substance in there. So even the rocks themselves would be heterogeneous mixtures. Homogeneous mixtures, on the other hand, when we look at them by our eye, we can't tell, unless we know the history, if it's a mixture or if it's just a pure substance that hasn't been mixed with anything. On the particle level, that's because the mixture is made of particles that are so fine, the most basic particles of a substance, that they intersperse amongst each other, so you just can't tell where they are anymore. It just looks like a sort of a mixture of the two colors or shades to our eyeballs. Examples of that, maple syrup would be a good example. It looks like a pure substance. If you look at it with your eyeball, you can't tell that it's made of many things, but we know that it's sugar and some kind of oils that make it taste like maple. All those things are in there, and also a lot of water. Kool-Aid is another example. If you just saw a glass of Kool-Aid, you wouldn't be able to tell just visually if it was a mixture or not, because it looks like all one substance throughout the whole glass of Kool-Aid. But if you know the history of making Kool-Aid, well, you know that that packet full of stuff and some sugar and water all went into the mixture. Here's a kind of a surprising one maybe. gold jewelry is usually not made of pure gold. It's usually something that's called an alloy, which means another metal has been mixed in with it. And the particles of the two metals, in the case of lots of gold jewelry that's silver and gold, those particles, the silver and gold particles, are interspersed within each other so completely that it just looks like one kind of metal. Mixtures have to be made out of something, however, so this is not the whole story of matter. Part of matter, in fact, most of the matter that we experience, is in the form of mixtures, which we can categorize as either heterogeneous or homogeneous. But the mixtures have to be made out of pure substances. Let's take a look at one way that we can think about pure substances. We can think about something called elements. Here's an example of an element. Carbon is an element. One of the most common forms of carbon is charcoal. So here's a pile of charcoal. And if you looked at charcoal up close at the submicroscopic level and could see the particles, you'd see what solids are typically like. Particles are structured and compact. It turns out that there is nothing you can do, there's no technique that you can do that will separate carbon into anything that isn't carbon. This is the most fundamental kind of matter that there is. Another example of an element is oxygen. You've heard of oxygen before, I'm sure. You breathe it, we need it to live. And if you could look at a sample inside this oxygen tank, you would see particles that are spread out because oxygen is a gas. And they would probably be moving rapidly, not in any kind of a structure. But again, like carbon, oxygen can't be broken down or separated into anything that isn't oxygen because it's the most fundamental kind of substance that there is. It's an element. Helium is another example. Helium is inside balloons, and if you look inside of a balloon, if you could see at the submicroscopic level, like oxygen, you'd see gas particles spread apart widely from each other. Aluminum is another element, one of those basic building blocks of matter that can't be decomposed or transformed into anything else other than aluminum. It's a solid, so you'd expect to see compact structure among the particles. Same thing with gold. This is also an element. Pure gold, not the kind that jewelry is made of, is an element. And at the particle level, it would be structured and compact like all solids. Copper, another example of an element. It's a solid, so you'd see that compact, structured arrangement of particles. Iron, another element. Copper and a gold and iron and aluminum are all what we call metals, and they have characteristics that are different than oxygen and helium and carbon, which are called non-metals. Here's one that you may not be familiar with. Sulfur. This is a pile of sulfur powder. It's a yellow substance. It's often responsible for things smelling bad. Sulfur is a solid, so if you could look at the submicroscopic level, you'd see structure and you'd see compactness. Now you might be wondering why I slid all of these elements, little squares, into weird places on the screen, and the reason for that is because those are the places that they belong in this periodic table. So a periodic table is a list. It's a really organized and structured and very sophisticated list, but it's a list of all the elements. There are a little over 100 of them, and many of them are not natural to our planet, but a good part of the periodic table is. And it's things that we have heard of before, like hydrogen or calcium or sodium or chromium, zinc, chlorine. All of these things are elements. If anything has its own square on the periodic table, that means it's a pure substance and it's an element, which is the most fundamental building block of all matter. You can't break elements down into anything simpler because they're as simple as it gets. We're going to take a closer look at two of the elements that we were looking at, iron and sulfur, and we're going to make a mixture of the two, and then we're going to do something else to them that goes beyond just mixing them together. Now I'm going to take the mixture and I'm going to apply some energy to it through heating. So I've got a burner here. I'm going to light, and then I'm going to just put this in over the burner. Before I do that, just for my own protection here, to keep a lot of sulfur fumes from coming out of here as the sulfur begins to melt, I'm going to stuff this glass wool into the top of the test tube. First I've got to ignite my burner. And I want a nice hot flame for this. But first I'm going to start out with a kind of a gentle flame. Just to make sure that I get the glass warmed up a little bit before I start to really get the mixture going. I don't want to create any cracks in the glass, because then the sulfur leaks out and the light's on fire and it just becomes a mess. So if you're looking closely, if you're able to look closely, you can see that the sulfur is beginning to melt and turn to kind of a brownish color in some places. And I think it's time to make this flame hotter now. So I'm going to add oxygen and get it heating up even more. So I have an orange glow inside the tube. And I can take the flame away, and that orange glow continues to spread. The reaction is now producing its own energy, as that's part of the chemical change that's taking place. So this is kind of like lighting a fire in the fireplace or a campfire. At first you have to use a match to apply some energy, but then once the fire gets started, it makes its own energy, and you no longer need to keep holding the match there. Okay, so the glow has died away and the change is done happening. So we're going to wait and let this cool down for a while, and then we'll get that out of the tube. I'm going to extract this substance out of this test tube. Not a very high-tech thing to do. I'm just going to break it. So I'm putting it inside this paper towel to sort of keep things from flying all over the place. I'm going to smash it with this rubber hammer to get out the substance inside. And what we see is something that looks a little bit like iron, but not exactly the same as iron. And it also does not look like sulfur. It's not as hard as a piece of iron would be. I can break it with my hands. And when I test it to see if it's magnetic, I am no longer able to pick it up with the magnet. So unlike in a regular mixture, where the properties of the parts of the mixture are retained, like magnetism for iron, or in sugar water, you can taste the sugar even though it's in a mixture. When this reaction takes place, this change, by heating it up, we were able to make it into something that does not have the properties of the original substance that we mixed. So here's what was happening during that change that we just observed. At first, we had a mixture. So that means that we had individual sulfur particles and iron particles. And remember, these are particles made of particles. So clusters of the small particles of the two elements, iron and sulfur, were gathered together in a solid form in that test tube. Then when we applied some energy through heating, in the middle stage there, we saw this orange glow happen inside the tube. And what was going on was the sulfur was melting, the iron particles were beginning to move around, and it released enough energy that it actually melted the iron particles apart, and they all started mingling together like they were one big liquid mixture. By the time it was all done, when we got to the point where we had that gray substance in the bottom of the tube, the iron and the sulfur had reformed into what we call a compound. So a compound is a way of putting elements together kind of permanently. None of the extraction or separation techniques that we use, like filtration or dissolving in water, distillation, none of those techniques would work to take this apart. So this is a new sort of matter. It's made of elements, but it's also a pure substance. This compound of iron and sulfur is something that is a pure substance. We noticed in forming this compound that we lost some of the characteristics of the things that we made the mixture out of. Like we couldn't see the yellow sulfur color anymore. The iron was not really visible. It was not quite the same color as the iron powder. And also the iron lost its strong attraction to the magnet when the compound was formed. So clearly we have another type of pure substance besides elements that we have to categorize. We saw an example where we took iron and sulfur and we put them together and then added some heat energy so that a reaction took place. We created a compound. That compound, this looks a little bit different than the one we had when I did it. It's a little bit shinier and a little bit more gold colored. This is an iron sulfur compound. It's pretty much the same one that we made. It's called pyrite, and pyrite is often called fool's gold, and you can see why, because it looks like it could be mistaken for gold. Because this was a compound, it had particles arranged in a structure, but it wasn't just one kind of particle. The particles of sulfur and the particles of iron were permanently joined to each other to make something completely new that didn't have the properties of the original substance. So we can modify our pure substances part of the chart by adding compounds to elements, because we now know there are two classes of pure substances. Compounds are made from elements, and they're made from elements not just by mixing them together. On the right-hand side here under elements, we have hydrogen and oxygen particles. They're mixed together. There's no reaction that has taken place that would cause this to become a compound. But by adding a little energy and then releasing a lot more, we can form this compound here, water, H2O. We organize the particles. You can see that they're arranged in a particular pattern. It's 2 H's to every 1 O. It's not just random, and it's not whatever happens to be the way we mixed it together, like a mixture. Compounds only put together the particles of the individual elements in a certain ratio, like H2O. Why do we know that it's H2O? That's a really good question, and we'll have to answer that at some point. Here's another one. Carbon, like from charcoal, and oxygen are shown here in a mixture, just kind of a random collection of particles. If you add some energy, and then you will release some more energy, you can change this. You can transform the carbon and oxygen to where they're not really individual elements anymore. They are now a compound, carbon dioxide, or CO2. You can see that there's a specific ratio of red oxygen particles to black carbon particles. That's characteristic of a compound. And another thing that's characteristic of a compound is that we cannot separate it again by using a physical means. We're going to have to do a chemical reaction that actually tears apart the carbon and oxygen chemically and turns it back into individual elements. That's going to require the addition of energy and a more complex process than just mixing or unmixing. So when we put this all together, this is the way we can sort out all matter. Most matter is mixtures, which are either heterogeneous, which means we can tell by eye that they're mixtures, or homogeneous, which could be mistaken for pure substances because they have the same form throughout. All mixtures are made of pure substances, and pure substances are either elements or compounds. So everything's made of elements. Elements form chemical combinations called compounds, but they can be mixed together physically as well to make mixtures.